We're going to go through this topic and we're just going to talk about what kinematics mean, what are the kinematic laws, and then we're just going to discuss how we can use them to our advantage. So let's go have a look first at what we were doing last time, or the last couple of lessons. The last couple of lessons have been spent looking at motion graphs, as you can see here. We then did, last Thursday, we spent some time talking about the position time graphs and how we can set them up. Sorry, no, last Thursday we spent some time talking about the EPI, which is the practical investigation. And we spent a little bit of time talking about, oh, well, this is what the difference between reliable data and valid data. Reliable data means that you have multiple data sources and an average. Valid data just means that what you're trying to measure can be measured by your system. Now, after lesson 55, which I believe we spent Friday doing, oh, that's right, we did a practical on Friday. That's why there isn't a lesson here for that lesson, because we did a practical and we explored different types of motion and how they work. And after we did the practical, what we did is we finished up with, after we did the practical, we finished up with a little bit yesterday on just giving you guys a chance to catch up on 9.2 and to do a neat for me, which was a useful test, a quiz, just to see where you guys are at. It looks like most of you guys are ready for the next topic, so we're going to start that today, which is kinematics. Now, these ideas of acceleration and displacement and velocity, they can actually all come together. We can actually talk about all of these ideas together in one. And kinematics allows us to sort of like break down these ideas into formulas. And we actually can create 5 formulas or 5 kinematic formulas. And we're going to go through them today just so that you guys are familiar with them. Again, some key concepts that I want you guys to keep in mind for this is that firstly is direction. Whenever we talk about direction, you're going to have to pay close attention to whether it's positive or negative. The second thing I want to introduce you to is the book doesn't use X for displacement. I did tell you at the start that we're going to use X as displacement. The book uses S. Now S, I figured because we haven't used displacement much, it wouldn't make too much of a difference, but I thought I would just quickly alert you guys to that now, just so that you guys can be ready for it when you see it. So first, let's start with the basics. The very first law we're going to talk about is going to be this one here. Where is it? So what is kinematics? Kinematics is all about using these equations of force, but we're not interested in, oops, he's broken something here. We're not interested in force. We're not interested in how much force something has. We're just interested in the amount of motion. And the second rule, and this is actually a pretty important rule that some people sometimes forget, our equations always assume a constant acceleration, which means that if you are speeding up, you are speeding up at the same rate the whole time. Okay? So we're going to talk about these laws. We're going to talk about the very first law that we're going to talk about is actually a law that we've been using a fair bit already. The law deals with the change in velocity. Now the change in velocity is delta V is acceleration over time. You might be familiar with acceleration equals velocity over time. This is that same formula being rearranged. Okay. Now, once you rearrange that formula, right, what you can do is you can then use that formula to say, well, if delta V is the change in velocity, then that means your final velocity, whatever your final speed is, whatever you're traveling at the very end, is going to be whatever you're traveling at the start plus a change in velocity, or your changed velocity. If your changed velocity happens to be negative, if you've dropped a value, drop speed, because your acceleration is negative, then that will mean your final speed will be this minus this, because it's a negative change. If it's a positive change because you're faster, it'll be plus this value. What that does is this gives us a formula. Final velocity, we're going to use the symbol V. Initial velocity, we're going to use the symbol U. And change in velocity, well, we've already got that written up here, AT. V equals U plus AT is our very first formula to calculate kinematics. So that will be the first one I want you to write down. The reason I've got this slide here is to show you how that formula was created. And in fact, we've got another slide to show you how a different formula was created. I'm going to do that in a second. So just, I'm going to give you a fraction of time to copy this down if you want to, or to take notes. And then, ladies and gents, I'm going to try something. This might not work, but I'm going to give it a try. All right. Let me know. Can you guys see a calculator, perchance?
Yep.
Cool. Hey, it worked. Hey, because I haven't got my Wake on board, this is my janky method of sort of going through content. It is literally like, if you guys could see this, you'd be like, what the hell, Mr. Greer? It is a bit of an insane setup, but it works. We're going to go through one more of these derivations. Now, a derivation means how you find out something. It's like a proof. I wanted to show you guys this, right? We're going to talk about we're going to do a velocity time graph, right? Here is our velocity time graph, yeah? Now, we're going to do something with a constant acceleration, okay? So if it's a constant acceleration, that means that the line on the velocity time graph has to be straight, because it has to change it has to have a steady gradient. Otherwise, it wouldn't be an acceleration. So we're going to do an acceleration in our picture that looks like this. Okay, so what we've got is, after a certain amount of time, the velocity increases in speed. It's gone from a low velocity to a high velocity. It has accelerated. Now it's actually accelerated at a constant rate. It's not speeding up like this or starting off fast and slowing down. It is a constant straight line. And that works with our laws. It has to be a constant acceleration. So is there any information that we can gather from this graph? It turns out there is. Let's say that this point here at the very, very top of this line here, let's call that V, because that's what it is. It's the final speed. Okay? Let's call this down the bottom, this one down the bottom, we call this u because that's our initial speed. So we're already traveling at some speed. Maybe this is 10 meters per second, maybe this is 60 kilometers an hour, and then we've changed to a higher speed, so maybe 100 kilometers an hour. Just from 60 to 100 kilometers an hour. We've done that in, like, I don't know, say like 10 seconds or something. So here's the question: what can we find out about this graph? Well, we could find out the gradient of this line, but that's not actually what I want to do. But if we found out the gradient of the line, you know, we went rise over run, so v minus u to get the rise over the run, which is t equals a, we would actually get v minus u equals at. We actually end up with v equals u plus at. Oh, we've got back to that first formula that I just showed you by finding the gradient. Remember, the reason that this is the gradient is because if you think about it, v minus u is the same as saying y2 minus y1 over x2 minus x1. So, nope, hold on. Next time. Now, the next part is, well, then what else can we find out? We found out we can find out, well, that's easy. That's one way we can get, that's a graphical way of getting that first law. What else can we find out from this graph? Well, we could find out this. This area under the graph represents something. This area under a velocity time graph, the area under a velocity time graph, that's going to be your displacement. Displacement in this time is called s. I'm going to write displacement in brackets here so that you, in case you forget. So that's our displacement, is this green curve here. So how can we calculate this green curve? Well, there are a couple of ways we could do it. We could saw this shape into two and end up with a triangle and a rectangle. But the easier way is to instead imagine it as a, can anyone tell me what shape this is? This green triangle. What shape is that? Come on, guys. Some input. You can write in chat. Rhombus? Ooh, good guess. Thank you, Kelvin, for giving a guess. But unfortunately, it's not a rhombus. It is a quadrilateral, though, so you're on the right track. What shape is it?
Kite.
Square trapezium. It is a square trapezium, yes. Does anyone know the formula for a square trapezium? You guys are all at your laptops, so someone can look it up. What is the formula of a trapezium? Half a plus b times h. Thank you. It is half of a plus b times h. In this case, a is this symbol at the top, b is this line at the bottom, and h happens to be this line here. Now, if I think about this, this a, oops, sorry. No. Oh, thank God. Now, if I think about this a here is the same as this distance between here and here, which is the same as u. Okay, so that means a we can replace with u, and b is the distance between here and here, which we can actually see is this idea here, that's v. So I can replace b with v. And this h is the distance from this line to this line, which we can see is actually t. So that actually gives us this formula here. I'm going to put this formula down here. S, which is the area underneath this trapezium, is equal to u plus v all over 2 multiplied by t. And that is our second formula. Now, if u happen to be 0, that would be actually just one more thing. Let's just pretend that u was 0. We started off going at like this. So u is here, v is here, here's t. The area would be the area under a triangle, which is going to be half of the base times the height, which is going to be half of the base, which in this case is t, times the height, which is v. And if you look, if you substitute 0 into that equation, you will get the same value. So this brings us to our second formula. So if we've now got 2 formulas, what are the rest of them? Okay. Okay, so someone's just thrown up a question to me. This person has left this question in private. It's not everyone can see it, but I will answer this question so that everyone can say it. So if I recall correctly, I remember you said the area under the velocity time graph is the distance traveled. Does that mean in this case the distance and displacement is the same, like traveling at a constant velocity? How do I do this? How do I explain this? Okay, so the technical answer is, and I actually will try and explain this properly. You know what? I normally would regret doing this, but I think this is actually pretty important. If I was to do this, so here's how it works. The area, in this case, if I draw, if I've got a velocity time graph here, the area under this velocity time graph is the distance traveled, and it is the displacement. So as you said, oh, it's also the displacement. The reason the confusion here was at the start is like, oh, but I said that, the displacement and the distance are only equal if you're traveling in like the shortest path. And that's sort of what's being assumed here, that you're traveling always in the direction away from the object. In a velocity time graph, because we're dealing with velocity, this is actually the displacement. When I said, oh, it's the distance, it's like, well, yeah, but it's usually the displacement is actually the technical word. The reason sometimes you get into a little bit of trouble, and the reason that I'm actually taking the time to do this, is if you get something like this. Now, in this velocity time graph, okay, and this is a problem with if you're doing year 11 and you're doing like integration in methods, this is going to be like, oh yeah, it makes sense. But if you're not doing it, then it's not going to make sense. If I wanted to know the total distance traveled for this whole journey, so initially the ball or whatever it is moving forwards, it gets slower and slower and slower, and then it stops for fraction seconds, and then it goes back the other way. If I wanted to find out the total distance traveled, I would find the area of this one, and I'd add it to the area of this one. But if I wanted to get the displacement, that's where you're going to have a bit of a problem. the displacement is actually equal to area 1 minus area 2. You might be like, what, hold on, why? Well, think about this. Area 1 is the distance you move away, whereas area 2 is the distance moved towards. So what you would have to do is you'd have to say, well, let's just say you end up moving 20 meters forward while you slow down. And then in the second half, you only move 15 meters. You move 15 meters in the negative direction. So you move 15 meters back. So that means your total displacement is 5. Whereas your total distance traveled is 35. And the reason that this might make more sense to someone that's actually doing methods is because you guys can probably see that that's the difference between finding the area under each of the curves versus just integrating across the whole thing. Because when you integrate a negative, this becomes a negative area and subtracts it. I feel like I've confused you guys more. You don't need to do methods to be able to do this, to do physics. All you need to really understand is this. The displacement is the area under the graph. And I will pretty much always give you guys graphs with just positive. The velocity is always in the positive. But yeah, that's what it means. Is I guess distance and displacement can be the same thing, and the area under a velocity time graph is the displacement. Let's jump back over to here. Hopefully I answered that. I feel like instead of answering, I've answered that. However, I do feel like instead of helping you guys out, I probably made you guys more confused. But here's the same idea. So this area under the graph is the displacement. So that means that, and it's a trapezium. So what are the 5 laws of kinematics? What are these 5 things that I've been talking about? Those 5 variables are shown here. These are the 5 equations. The first 2 we just made up on our own. The last 3 are actually the first 2 with substitutions that have happened in them in order to create them. What's a boring Sunday, and I've never actually done this properly before, but a good boring Sunday activity is to take each of these and try to make the other ones. So I think if you like take this one and then if you take the second one and then you expand it and then you change V and you substitute the first one in, you can actually get the third one. And then I think if you then substitute it in differently, you can get if you take the first one and substitute it for U, you can get the 4th one. And then I don't know how you get the last one, but you can make all of these and derive them. That's something fun you can do, but I don't necessarily know how to do it off the top of my head. So I'm not going to try. Now, the importance of the kinematic formulas, again, remember, they only apply to straight lines. So you're moving straight lines forward and backwards, and they only apply to, and that's why we can get away with saying the displacement is the area under a velocity time graph, because you're moving in straight lines. And the other thing as well that this also considers constant acceleration. That acceleration can be 0, but it's still constant acceleration. Now, the reason there are 5 formulas is because each of these formulas is missing one of the variables. The first one is missing S. So you can actually calculate this formula. You can use each of those as even when you don't have S. The second one doesn't have A. So you don't need to know the acceleration. You can still work out all these things. The third one and the fourth one don't use V and U respectively. And I find the third one and the fourth one the easiest ones to remember because they're just the same as each other, except you're replacing the u with a v and when you're changing the sign. And it sort of makes sense in my mind. I haven't actually really properly explored it, but for some reason it's like, oh, you take your initial velocity and you add the acceleration. That's what you're doing, is you're taking your initial velocity, you're adding the acceleration. This is sort of, I believe, represents the average change in velocity, whereas this one, when you take your final velocity, you need to minus it. It sort of makes sense to me. But regardless, these will be provided to you guys as a formula sheet, but you should still have them all written down. The rest of this lesson, what I've got now to do is I've got 4 examples. I'm going to push through all 4 examples. These are examples that are taken straight from my engineering math subject because I was running a bit short of time. So if you've done that before, you've seen these examples before, you might remember the answers. If you haven't, then, you know, well, that's something you might have to look up. But we're going to go through them anyway. At the very end of this, I'm going to give you guys a chance to work on 9.5, which is going to be the last one in chapter 9. And then after 9.5, after this week, we're going to start talking about forces. And so we're going to start bringing forces into play here. And what does that mean for our situation? So let's start. Now, I'm going to be switching between this and the pad as time goes on, but we're going to read this first. And if you guys want to have this open up in a separate tab, so you can like maybe look at both of them at the same time. If I'd have been smart, I would have printed these off. That would have involved hooking my printer off, and then I could have worked in them under the camera, but unfortunately, that requires a little bit too much organization. So a car is starting at rest and accelerates at 20 meters per second squared for 30 seconds. How far will the car go in that time? So the first thing, by the way, quick heads up, whenever you see the words starting at rest or coming to rest, that means rest means 0 meters per second. If you're not moving, you're at rest. So that's what that value means. Let's do this. Now, this is actually working surprisingly well. Okay, so how do I do a question like this? The first thing you should always do is, first write down all of the relevant facts. So for me, a car is starting at rest. So starting at rest, that means its initial velocity is at rest. So its initial velocity, or u, equals 0. That's the very first thing I write down. And it accelerates at 2 meters per second squared. Okay, accelerates. Oh, well, that means your acceleration is positive 20. It's speeding up. Cool, perfect, okay. For 30 seconds, hey, time equals 30 seconds. How far will the car go in that time? Okay, so they're looking for S. Okay. Now, they also haven't given us one of the 4 things. What haven't they given us? They haven't given us the final velocity. So we need the formula that has U, A, T, and S in it, but doesn't have the final velocity. So I'm just going to quickly draw them up over here. V equals U plus AT. Well, that's got V in it, so it's not going to be that one. What's the next one? S equals U plus V over 2 times T. Well, that one's got V in it. So it's not going to be that one. Let's see. S equals UT plus half AT squared. Hey, there's no V in it. All right. Okay. Have I got the other values? I've got U. Yes. Have we got A? Yes. All right. That looks like I've got T. I've got S. Yep, this is going to be the one that I'm going to use. Okay, so let's write down the formula. S equals UT plus half AT squared. Now, here's the question for you. Do I need to rearrange this formula?
No.
No, I don't need to rearrange this formula. This is perfect. I can just plug the values in. The values being U, which is 0 times T plus half times 20 times, in this case, T, which is 30 squared. Well, sorry, technically this T is going to be 30, but 0 times 30 is 0. We have 0 plus 10 times 30 squared is going to be probably 900. Right? Surely, yeah. Maybe 9,000. 30 squared times 10, 9,000. 9,000 meters. It says how far will the car go, so that's actually good enough. I don't actually need to work out. I actually don't need to work out like a direction, but if I did, I would probably just say forwards. But it doesn't matter too much because everything's lined up perfect. That's how you use the formulas. And let's go through the steps that I did. Step 1. You should do this with all questions, is extract the information. Any question in maths or science, you should extract the information. This might be a list of values, it might be a picture, whatever. Then I went over to my list and I said, well, which one of my variables, which one of these am I going to choose? I have to be the third one. And then I substituted it in. Keep in mind, units are going to be, sometimes you need to be careful about units in these types of questions. You may have to worry about, and also if you're super lucky and you get all 5 of these, it actually won't matter which formula you use, as long as you use a formula that has S in it so you can work out what S is. But if you get given all 5, it's very rare that they'll do that. Let's jump into question 2, and then we'll, there's a question here in the chat. Okay, yeah, now Kelvin was helping me out because I was a bit trying to do it on my own, but yeah. Let's go have a look at here. So question 2. A motorbike was moving at 22 meters per second when it stopped, and it took 18 meters to stop. How long did it take to stop the motorbike? Okay. So this is another one. What I want you guys to do first is I would like you, before I do it, I would like you to look at this question and see if you can extract all of the important values. So the V's, the U's, and everything like that. Okay. Let's do this. Nope. Shit. My janky ass thing almost fell over. Careful. Okay. So the second one, which is in some ways is a bit easier. So motorbike was moving at 22 meters per second. Okay, if it was moving at 22 meters per second, then that means that that's going to be a relevant idea. If it was moving at that, then that probably means that that's the first value. So that means I'm going to write that mu equals 22. Perfect. Okay, sorry, the focus is having a freak out session, but it should be fine. Okay, when it stopped. Okay, well, if it stopped, what's its speed going to be when it stopped? Thoughts?
0.
0. That means that its final speed is going to be 0. And that's an important thing to look out for, because it's important because it helps you guys look at, okay, well, what does that mean? It came to a stop. That means that's a value, that's an idea. And it did so in 18 meters. Okay, what does that mean? It took 18 meters to come to a stop. What does that actually mean?
Distance travel.
Yeah, the distance traveled is 18. S equals 18. Now, it just so happens that might be important for you guys to recognize that if you are stopping, right, then your stopping distance is going to be in the same direction as your initial speed. So both of these are positive. The reason that both of these are positive is because your distance that you travel forwards is in the same direction as you were initially traveling forwards. And that's going to help for the next question. It's going to be a bit important. The last question says T, how long does it take to stop? Okay, so now we've got U, V, S, T. We haven't got A. So we jump over to our formulas. Which one are we going to use? Well, this one's got A, so we're not going to use this one. This one hasn't got A in it. What do you know? That's going to be the one that we're going to use. S equals U plus V all over 2 times T. Question, does this one need to get rearranged?
Yes.
It does, because what we want to calculate is we want to calculate T, and T is on the wrong side. So how we rearrange this? Well, multiply both sides by 2, which gives us 2S equals U plus V all multiplied by T. And then I'm just going to divide by this whole thing here. So that ends up with, or you can just move that to the other side. We end up with 2S all divided by U plus V equals T. 2S is going to be 2 times 18 all over, in this case, U, which is going to be 22 plus 0. So we've got 2 times 18 divided by 22 plus 0 is going to be 1.6. How many this? Yeah, we've only got 2 significant figures. I'm going to go with 1.6 seconds. Done. Questions about that one? So let's go through the process again. Step 1, extract the information. Step 2, choose an equation. Step 3, rearrange that equation. We didn't need to do this with this top one, but we do with this one. Rearrange the equation. Step 4, solve. So those should be the same sort of ideas that we always do. Okay. So now let's go back to here. Question 3. Question 3 says that a person was falling through the air at 20 meters per second. He pulled his parachute and slowed down to 18 meters per second after falling 20 meters. What was the person's acceleration? Okay. So firstly, I want you guys to do 2 things first. I'm going to give you 2 minutes to do this. I want you to write down all the important information and then choose which formula we're going to use. Go. All right, here we go. So, second last one. Okay, so in this one, we have a person is falling through the air at 20 meters per second. Okay, falling through the air at 20 meters per second. That gives us an initial velocity. So I'm going to do this up here in this corner. We're going to go for blue this time. So U is 20. Now, because I've said 20, I'm actually going to say positive 20. But because I've done that, I have to do something really important, actually. And I'm going to say this up in the top here, just so for records, I'm going to say positive equals down. And that's going to be important later on. Okay? Normally what we've just had so far was just had, oh, it's going in this direction. I haven't said which way we're going, but this time I need to say, oh, just for warning, positive means down. Now, our final velocity, he slowed down to 8 meters per second. But it's still positive, like it's still going the same direction. Okay, he's not going 8 meters per second up, or the person's not going 8 meters per second up. They're still going in that same direction. And it takes 20 meters of fall to get to that new speed. So that's plus 20, because it's going to take us 20 meters. The direction that you're falling is downwards, like the distance that you've fallen is in a downwards displacement. If you were to go your displacement over time, if you're going to go your displacement, you've gone up to down. It's a downward displacement. These are going, this time spent worrying about signs is going to be important for this question, but also future questions for you guys. You guys, the most common way people get questions wrong is they're like, oh, I don't understand. This question doesn't make sense. And it's like, usually I will take 2 seconds looking at the questions like, oh, That's because you've said up is positive, but then you said gravity is also up. And it's like, oh, whoops, you know. What is the person's acceleration? So we're looking for A. Now, hopefully you guys looked at this and you said, well, therefore we don't have T. Which of our formulas doesn't have T? This one at the bottom. Now, hopefully you guys got that far in that short amount of time that I gave you. But if not, that's okay. We're working through this together. So we've done step 1. We've got the information down. We've done step 2. We've chosen a formula. Next step, step 3, is to write down the formula v squared equals u squared plus 2as. And the question then becomes, do I need to rearrange this formula? I'm asking that to you guys.
Yes.
Yes, I do, because I want to calculate A. So we're going to put A on by itself. To do that, we need to get rid of this u squared. So we're going to do that by subtracting u squared from both sides. V squared minus u squared equals 2as. I'm just going to divide both sides by 2s now. V squared minus u squared divided by 2s equals A. All right, now I've got a formula. And it's been rearranged. All I need to do now is a quick little bit of substitution. V squared, which was positive 8 squared, minus u squared, which is in this case 20 minus 20 squared, all over 2 times, in this case, s is 20, 2 times 20. 64 minus 400 over 40. Negative 8.4 meters per second squared. Now, let's have a little bit of a look here. Now, why is this one interesting? Because we've got an acceleration that's negative. That means we are going the acceleration is 8.4 meters per second squared. The negative down is positive, then we are going 8.4 meters per second squared up. And that's important. Understanding what that is important, and sometimes you'll have to pay attention. That positive is opposite the direction of that negative is in the opposite direction of the velocity. So that's why we've slowed down. The acceleration is upwards. It's actually pushing us up. And that's why our velocity gets slowed down. If we were talking about force now, I would then get you to go, hey, the reason there's an acceleration upwards is because there's a force upwards, which is the air resistance force. All of these things are important. So that's why I think it's pretty important for you guys to pay attention to that's why it's pretty important for you guys to pay attention to signs. So make sure that you know what you're doing. If you're like one of the classic ones that I have is there'll be a velocity downwards, but you're like this, you know, it might be your final velocity might be downwards, but your initial displacement may be upwards or something like that. So make sure you keep your directions in place. Again, steps were extract the information, choose a formula, rearrange that formula, substitute for an answer. We've got one more question, which is probably the hardest question that I've got, but we're going to give it a go anyway. Let's do the last question. There is a question in the chat. Maybe it's just a so 20 squared is 400, maybe whatever. But let's have a look here. In the chat is, are you allowed to have a negative and up in the same line? E.g., no, you cannot. So the question was, can you have a negative and an up? It's like, well, no, the problem with that is, and that was actually one of the questions in the quiz, if you say negative, it's like saying, oh, I walked negative 20 meters east. That doesn't mean that you've moved east. That means you've moved negative 20 meters east, which means you've moved 20 meters west. So you essentially, by saying negative 8.5, right, negative 8.4 meters per square up, I would be doing a double negative. That's why I either say negative 8.4 meters per second squared, because that's the opposite of down, or I instead write down 8.4 meters per second up. So just keep that in mind. That the sign at the front also is a way of giving you a direction. So last question. I'm sure you guys are getting, let's go back here. The last question is the hardest question, but heck, you know, you guys are in year 10 physics. You guys can handle that. Year 11 physics even. You guys can handle a hard question. Okay. A truck speeds through a red light at 2.8 meters per second and keeps this speed. A police car at a red light catches up at a red light, chases after it, and accelerates from rest at 4 meters per second squared to catch up with it. How long will it take for them to meet? Okay. So, how do you do a question like this? So, this one's a bit more challenging. Again, excuse me, write down all the important information now, guys. You've got a minute to write down as much information as you can. I'm going to show you guys a couple of ways you can actually tackle this question. This is a difficult question, but it all depends on how you visualize it. Let me kick you out of the room. You keep barking. Okay, here we go. So, last time I connect to here. Also, by the way, be aware that some situations aren't physically possible. I found this out the hard way. I was trying to write a question a couple of years last year. I was like, oh, if I've got an object that falls this fast instead of this, get out, get out. You can keep it out of the room, man. Go on. Sorry about that. So I found out that there was a couple of situations where it's not physically possible. Like, for example, you can't accelerate faster if you've got like two distances and you say, oh, I'm going from this velocity to this velocity, and then you're saying, oh, but I'm doing it in this acceleration. That might not actually be mathematically possible. So let's grab a look at this one. How do I do this? Well, I'd read the question. A truck speeds through a red light at 28 meters per second, keeps the speed. A police car at rest chases after it and accelerates from rest at 4 meters per second squared until they catch up. What does this look like? That's what I would. Now I could try and extract the information. Let's try and do that first. I'll see where we get stuck. Okay. So the first reason that this becomes hard is because you're okay. Well, let's do the truck. The truck has an initial speed of 28 meters per second, and it doesn't accelerate. So that means that, and it keeps the speed. So that means at the end, its speed is also going to be 28 meters per second. If it keeps the speed, then the acceleration is 0. Okay. Now, we don't know the displacement, and we're not given the time it takes for the two of them to catch up. So these are all values that we're going to have to work out. Okay, but what about the police car? The police car has an initial speed. Well, it's sitting there at the red light, not moving. So its initial speed is 0. Its final speed is, well, we don't know what its final speed is. You might be tempted to say, oh, its final speed is 28. It's like, not necessarily. Because remember, it's speeding up to catch up to it. It's actually going to have to go faster than 28 meters per second to catch up to the truck. If it was going slower, it would never catch up. We do know the acceleration. The acceleration is 4. We also don't know S, and we don't know T. So this puts us in a bit of a weird situation here, okay? How the heck are we going to do this? Because you can see that we need to have 4 facts in order to, well, we've got 3 facts we can work out, but we haven't got enough information to work out anything really for the truck or the police car. Oops, sorry. So what I would normally do in this situation is I would try and see if there was another way that I could do it. I'm going to now look at this in a different way. I'm going to look at this over here. I'm going to try and graph what's going to happen, just so I can get a rough idea. So I know that if I've got the displacement and the time, I know that the truck is going to be going up like this. Okay? Because the truck's displacement is going to be increasing 28 meters per second every second. Whereas the police car has to catch up from rest. So it has to accelerate and get faster and faster and faster and faster and faster until eventually they will meet. That's an important factor. We want to know when their positions are the same. These two positions have to be the same. So what I would be tempted to do is to say, is there a formula that has U, A, S, and T in it? And there is. That formula is S equals U T plus half A T squared. And we want to know, when does this displacement, for whatever value of T we use, when does this displacement equal the displacement of the truck? The displacement of the truck can be calculated in exactly the same way. The displacement of the truck can be calculated S, and that's going to equal UT plus half AT squared. What's interesting as well, as you guys should be able to see, is, hey, we've got it squared. That's why this is curving up. But you should see with the truck, that's a bit weird, because for the truck, we know that the acceleration is 0. So that means that it's actually just going to be UT equals UT plus half AT squared. Now, if you're a bit confused at this point, don't worry, this is a pretty difficult question, especially because it's going to use some high-level maths, but I thought I would just throw this over to you guys anyway, just so you could see, well, what would happen. In this case, UT, in this, we're going to take this value up here for U, which is 28. A is 0. That's why, by the way, this cancels out. A reminder, A is 0, so that cancels out. So we end up with 28t on this side of the equation. On this side of the equation, u is 0. So that means this goes. We end up with half times a, which is 4, times t squared. 28t equals 2t squared. Which means that we're going to end up with 0 equals 2t squared minus 28, or dividing everything by 2, 0 equals t squared minus 14t. And then if I just go, okay, well, therefore, you know, that's going to mean that the only way for that to work is if t happens to be, how do you solve this? The last little bit is to do this. Take t out as a common factor, t minus 14, and then what that means is t equals 14 seconds. That is the time it takes for the police car to catch up. Now, this is a very difficult question. And I actually very much doubt that you get a question like this in 9.5. But why I'm doing this here is why I'm doing this here is because I want you guys to see how we can use our kinematic formulas to calculate something like this. The trick here that I always find difficult, even when I'm trying to remember how to do this question, is to be like, oh, well, which formula is it? Why did I choose S? The reason that I chose S to use is because I know that these two have to be the same. And that means I need to have S, and I need to use UA, and I guess, well, I want to know what T is because I want to know the time taken. So that tells me I need to use the equation that has this one, this one, this one, and this one in it. Okay? Now, it makes sense to use the same one for the truck, but you didn't have to. You could have used any of them as long as they had S, T, and yeah, as long as they had S and T in it, you could have used any of the other ones. We could have used V squared minus AT, you know, that would have worked too, but it just would have been a bit uglier. So that's how I got this one. Those of you that are massive nerds should also notice that the reason I made this 0 is because I used something here in maths called the null factor law. You guys might remember that these two values both equal 0. That means there is another solution which is t equals 0. Of course, there's a solution which is t equals 0. That's here. That's when the truck first passes by the police car. It's only until here at 14 seconds that they meet up again. Now, what I want you guys to do now is I would like you to now go and give 9.5 a try. I am going to give you guys during the week some more examples of 9.5 type questions. I'm going to do the same thing which I've been doing this whole time, because I'm going to keep this Zoom open for the next 20 minutes in case you guys have an additional questions that you want to shoot over to me because you're a bit confused about, you know, how to do this part of the question, something like that. So, and I'm actually going to keep my weird writing setup so that you guys can actually ask me questions. But 9.5. Later on in the week, I'm going to give you guys some more questions with kinematics because this is one of the areas that students struggle with, is trying to pull these apart. And if you can't do kinematics well, you're going to struggle with the rest. If there's no other questions and you don't want to stick around in the Zoom and you know what, one last thing we should do. Yeah, we haven't done this. Let's just quickly do this. Let's go through the attendance question. Yay! Because I bet you guys got that wrong. Maybe because I've hit you guys with the same type of question 12 times, you will have gotten it right this time. But let's have a look. there was a question that just popped up, but I'm just saying. All the questions in 9.5 events, I want you guys to start at the bottom and make your way through it. You guys need as much practice as you can get. I might end up cutting some of them later on, but at least the first few. So the attendance question today was, not the fancy ball question, where is it? Here. A person was riding their bike up. Can you guys see this? I'm not sure if you guys can see this. You should be able, yeah, you should be able to see this screen. A person is riding their bike uphill at 14 meters per second and started, whoopsies. And started experiencing steady acceleration downwards at 5 meters per second squared. After a certain amount of time, the cycle is traveling downhill at 3.5 meters per second squared. The time mentioned above is, the answer is 3.5 meters per second. You guys are doing a lot better at these questions now. But for those of you that want to see me do this one last time, because I know that you guys love it, we can actually do this really quickly now with a, we can actually do this super quickly now because we now have kinematics rules. So, initial velocity. Initial velocity was, the person's riding their bike 14 meters per second. A is against the direction that they're traveling because he's going uphill. So it's a positive. We're going to go positive equals uphill. Whereas the acceleration is downhill, so it's -5. Your final velocity is 3.5 meters per second downhill, so -3.5. Remember, up is uphill. So that means that, and we want to know the time taken. So we're looking at V equals U plus AT. In this case, we've got -3.5 equals 14 plus, take away 5t. We're going to go -17.5 divided by equals 5, -5t. Therefore, the -17.5 divided by -5 equals t equals 17.5 divided by 5 gives you 3.5. Yay! T equals 3.5. Perfect. I fell asleep, you missed that last little bit. But T equals 3.5 seconds. Cool. Alright, guys, now I want you to keep working on, to start working on 9.5. There are a fair few questions in it, so you guys have got plenty of stuff to work on. If you